A raw email dump turns headers and attachments into retrieval noise. Unstructured partitions each body and attachment into searchable elements with the metadata RAG needs. You'll learn how the pieces fit into a workflow that parses email with attachments and searches the combined evidence. I'm Professor Pi, teaching AI engineering and LLM systems with simple Python. Emails are messy. Routing headers, threading markers, inline replies, and attachments all arrive in one raw blob. For a RAG system, you want clean, labeled fragments with provenance, so a retriever can pick the exact piece of evidence. People reach for unstructured because it understands document structure and emits elements with categories and metadata that map cleanly into an index. At small scale, this cuts down manual parsing. At moderate scale, it saves hours of brittle heuristics and keeps attachment text discoverable. Intuitively, we turn one raw.eml file into a set of labeled pieces. Subject as one element, body as another, PDF attachment as a third. Each piece carries where it came from, so a query can ask for attachment-only results. The big win is fidelity. You don't flatten everything and lose the fact that some text came from a policy document. The trade-off is upfront normalization before indexing, which is a small cost for much more precise retrieval. We'll build a compact demo, read a tiny email, capture headers, parse a text attachment, convert elements into simple records, index them in Chroma with deterministic embeddings, and query so the attachment surfaces for policy questions. The goal is to show headers and attachments remain discoverable end-to-end, so a RAG prompt can include the right evidence. Quick note: this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. First, we parse a raw email string while keeping the headers as first-class elements. This snippet parses a tiny raw email string with unstructured partition email and keeps header evidence visible. Raw email dumps put routing facts beside body text. So the first job is to separate them without flattening everything into one chunk. Partition email reads EML text and returns elements whose category values distinguish subject from the body content. Include headers equals true, asks unstructured to emit headers as elements, while metadata still travels with each element for later filtering. The output shows how many elements were extracted and confirms the subject is searchable. That separation is useful, but many real emails hide the actual facts inside attachments. This example writes a real .ml file with a text attachment and parses it with unstructured partition email. The body alone says a policy update exists, but the attached policy carries the evidence a retriever may need later. Email message creates a small multi-part email. Then process attachments equal true tells unstructured to partition supported attachments along with the email body. Content source equals text plain keeps the example focused on the plain body instead of HTML. The output confirms that attachment text made it into elements, which is the key difference from body-only ingestion. Now that unstructured returns elements for both body and attachment, we need to turn those elements into compact records a vector store will accept. This code converts unstructured elements into compact RAG records with text, type, and file metadata. A vector database usually wants stable IDs, document text, and filterable metadata, not raw element objects. The loop keeps only non-empty text, uses eMetadata.toDict to expose the source file name, and stores eCategory so body and attachment content can still be distinguished after indexing. The record shape is intentionally small, but it mirrors the fields most retrieval pipelines need. The output shows the record count and the source files. proving the email and attachments stayed connected, with normalized records in hand. Next, we embed and index them so semantic search can find the attachment content. This snippet indexes the records in Chroma using collection.add and explicit embeddings. The ingestion boundary is now clear. Unstructured produced clean elements, records normalize them, and Chroma stores searchable documents with metadata. Embed is a compact teaching stand-in for a production embedding model, which keeps the example deterministic on screen. IDS, docs, metas, and ems are passed together, so every vector keeps its original text and file label. The output shows Chroma accepted the records, and that each vector uses the same 4-feature shape. Indexing gives us a searchable store that can prefer the attachment when it contains the authoritative text we need. This example queries Chroma collection.query with the same embedding shape to retrieve attachment evidence. The query asks for refund, manager, and approval, which should favor the attached policy over the shorter email body. Query embeddings keeps the demo deterministic because it uses the same embed function as indexing, and include requests the metadata and distance needed to inspect the hit. N results equals 2 would also let a downstream prompt include both body context and attachment evidence. The output shows the top source file and its distance, making the retrieval step auditable. In a real project, you'd swap the toy.eml for a corporate mail export, OCR attachments before partitioning for images, and preserve source file name and message ID metadata so auditors can trace claims back to originals. We parsed emails into labeled elements, kept headers and attachments intact, and indexed them as records so a retriever can prefer attachment evidence when it matters. Use this pattern when emails and attachments contain distinct, searchable evidence you can't afford to lose. One caution: element normalization requires consistent metadata handling, or you risk splitting logically connected text across unrelated records. A practical next step is to replace the toy embed with a production embedding model and increase the retriever end results to 5. So both body context and attachment text can be composed into a single prompt. That will improve recall for complex queries about policy and approval. If short, practical AI engineering helps, subscribe and watch the AI engineering videos.